Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is the third in the series on impulse and momentum, section 2, and it's about more complicated impacts involving more than two spheres. Let's just reprise the definitions. Firstly, we've got the coefficient of restitution. It's dimensionless. It takes a value between 0 and 1. It's an idealization of Newton's experiments, and there are the two special cases that E equals 0 is where the particles stick together, and E equals 1 where you have a totally elastic collision. Now kinetic energy has to be considered for all the objects, and we're interested often in finding the change in energy, and it's the final kinetic energy minus the initial. And if that turns out to be negative, that shouldn't surprise us, because in a collision we very often lose energy. So here's our first case, and you'll see it's more complicated. There are three objects moving in a line. The first one is catching up the second, but as things stand, the second one is going at the same speed as the third. B is the same speed as C, so there would be no collision between B and C without a bump from behind by A on B. So to model this situation, we need to introduce unknowns, and we need to consider it step by step. So we consider the first collision, where we'll have the usual two unknown velocities and two equations. So there's our problem drawn up with two unknowns, x and u, and we've carried the 3 forward because the third body, the C, is not going to change any speed since it hasn't collided. So in the usual way, we'll end up with the restitution law telling us that a half is equal to the velocity of separation, which will be u minus x, over the velocity of approach, which is 7 minus 3, that's 4. So that will tell us, multiplying by 4, that 2 equals u minus x. That's our first equation. Now we'll also have a momentum equation, and that will come from saying that the momentum before, which is 2 times 3, plus, that's for the B, I should perhaps have put the A first, so it's 1 times 7, plus 2 times 3, and that's equal to the momentum afterwards, which is 1 times x, plus 2 times u, plus 2u. So you see there we've got two equations in two unknowns. We could simplify the second one. 1, 7 and 2 3s makes 13, equals x plus 2u, and now we're set up to solve those two equations. So if we make the first one tell us that x is equal to u minus 2, then we can substitute into this new equation and say that we've got u minus 2 plus 2u, so that will tell us that 15 is equal to 3u, so therefore u is equal to 5. And on that basis, if we go back to this equation, x will be equal to 3. So that means to say we've decided what happens in the first collision. We can now draw up the x as a 3 and the u as a 5 and consider what happens with the second collision. So there's our calculations, and the original setup still shown, and we can move on using that information as solved here to draw up, consider what happens in this second collision, except that this time we'll allow for this 3 to change to something else as B bumps into C. So there we are, that's drawn up again. I've introduced a new V, and this time we're not expecting anything to change over on the left because A is falling behind, but we are expecting something to happen on the right. So again we apply restitution law. We'll have half is equal to the velocity of separation, V minus W, over the velocity of approach, which is 5 minus 3, that's 2. So that's telling us that V minus W is equal to just 1. So that's restitution law, and there's not much more to that. Momentum, I need a bit more space now, so I'll move down a bit. That's going to tell us that 2 times 5, the initial momentum, plus 1 times 3 altogether, is equal to the final momentum, which is 2 times W plus 1 times V. That's again an equation, two equations in two unknowns. So we've got 2 5s are 10 and 3 is 13 is equal to 2w plus 1v. Needn't put the 1 in, but I've got it there for good measure. So if we use the same first equation to tell us that v is equal to 1 plus w, then we can substitute and get 2w plus 1 plus w. So from that we can see that 12 is equal to 3w, so w is equal to 4, and if w is equal to 4, then v is equal to 5. So then we've got 3, 4 and 5, and that really establishes that we don't have any further collisions because the velocities are such that no one of those particles is catching up the one ahead of it. So there we are, that's the calculation repeated, and we can see that if we draw up the picture with the 3, the 4 and the 5, we can fairly conclude that because C is going faster than B is going faster than A, then there'll be no further collisions, which is what the question asked us to show. Now, as regards kinetic energy loss, it's the usual bank of figures. Notice that this is the kinetic energy of A, this of B, and this of C finally. And on the other hand, referring to the originals, this is for A, for B, and for C. Well, there's a lot of arithmetic there. You take it that my answer is correct. It's -5, and that tells us that kinetic energy lost is 5 joules. The question answered in context with the units. Well, that concludes the video presentation on successive impacts. The next one will be on successive impacts with a plane. I hope to be with you later to explore that.